All right. Well, hello, everybody. It's great to see you all, and awesome that so many people joined again for our VMOL Seminar series. It's the second round of our mzmine series, and yeah, thanks again, Ansgar, Robin, Corinna, and Stefan for doing the seminars with us. So today we're gonna continue with multimodal data analysis in mzmine, and yeah, it's my great pleasure to have Ansgar Korf give the seminar today. And before I give over to him, just a very brief introduction. Ansgar, the now CEO of mzmine, is an analytical chemist. He did his undergrad in food chemistry and business chemistry before then doing a PhD in analytical chemistry, also all at the University of Münster. He then worked for a couple of years at Bruker, where he was the product manager for the timsTOF. So if you have a timsTOF and you really like it, then I'm sure Ansgar will be happy to get some of that credit. But then, yeah, like very recently, he Robin, Stefan, and the others founded mzio, where he now leads the business operation there. And yeah, without further ado, Ansgar, thanks a lot. I'm looking forward to your talk.
Thanks, Daniel, for the kind introduction. Let me quickly set up the technical things. So can you see my screen? Perfect. Okay, I hope you see it now in full screen and you see some presentation slides. Perfect. Yes. Yeah, as mentioned, today we want to focus on different analysis techniques in a single software. First of all, I'd like to thank Danny and the VMOL team for organizing these seminars. I think it's great to have this presented to a global audience for many different tools, analytical tools in the field of mass spectrometry and beyond. And as Danny mentioned, this is a 4-part series. So 2 weeks ago, Robin already started presenting on LC-MS, focusing especially on how to perform proper feature detection, statistics, and molecular networking and compound identification with spectral library matching. And in today's presentation, we will also focus a little bit on LC-MS, but also merge into the other analysis techniques that are quite popular in all the laboratories across the world, which also have big challenges, which is GC-MS, especially electron ionization, and MALDI imaging. And for all 3 techniques, I want to focus on lipid identification. We will have 2 more presentations in 2 weeks. Stefan will talk more on ion mobility and contaminants and pesticides. And also don't miss the last encounter, which will be presented by Corinna. And there you can learn how to build your own spectral libraries with mzmine for LC-MS2 datasets, but also if you have the capability or your instruments has the capabilities also for MSN data. Before we start with the topic of today, one quick information how you can access mzmine. So mzmine has 2 licenses. If you work in academia, you can get a non-profit license, which is free of charge. And if you want to use mzmine these days in a company environment, you can obtain an mzmine Pro Enterprise license that unlocks the commercial use, and you also get exclusive priority support from the mzio team. If you want to learn more, just follow the link below. You will be prompted to this website, and you can either directly download and register for the academic program or get in touch with us. So jumping into the topic, the whole goal of mzmine these days is to be one software to manage all these different data modalities in a single software. And we all know from our laboratories, we have this wild mix of different sampling technologies with different MS technologies and mass detectors. On top of that, they come from different vendors, which means also different data type formats. mzmine wants to handle all these different types and formats, and also tries to be as high throughput and extract as much knowledge from these data. So the question is, how can we be still easy to use? Because we want to manage a lot of different data in a single software. So you can expect today three separate live demos, one on LC, MSMS and lipid identification, one on GC and one on MALDI Imaging. And before we start with the LC demo, I want to briefly go through the theory behind all the data processing for LC MSMS so that we can later easily compare it also to GC and to MALDI data processing. Okay, so for all these different data types, we always start with the raw data. So the idea is, or the goal is to go from the raw data to the final results, which are identified molecules in large studies. So we handle the raw data natively, we process the spectra, and today I will not go into detail for any of the ion mobility steps, but this is also possible in a similar workflow. What we usually do with the processed raw data, we start to build our first feature list, which is just a list of extracted ion chromatograms. And these ion chromatograms, they are then resolved into separate, as we call them, features. So a feature in this presentation is always a pair of retention time and M/Z. With this feature list, we can now do many things, and it's a good idea to add some more information early and also to reduce the feature list early. So for example, we can filter for isotopes, and we can also enhance the isotope pattern by searching for it. But the ultimate goal is to align different feature lists across samples. And during this alignment process, we can maybe have some gaps that could be due to how the data was acquired, but also due to processing artifacts. So we go back to the data and look for these gaps. And once we have this gap-filled feature list, we try to put as much information to the data as possible. We, for example, group the features by their peak shape to then perform ion identity molecular networking, so we get very clear ion notations. And with this feature list, we can then perform different annotation tools. For example, we can do spectrum matching. We can also use local compound databases for MS1 searches or for matching mobility, for example. And for lipids, we have a rule-based approach. We can then further filter the results based on many different criteria. And also, we can then use that final feature list to, for example, go back into the data. If we did not identify everything, we can perform, for example, molecular networking, statistics, and we interoperate with other great tools which are out there, such as Sirius or GNPS. Yeah, this workflow is extremely long, and it's very hard to remember and to have it in your brain and to set it up manually. Therefore, we have now implemented the MZ Wizard. And the MZ Wizard is a tool that makes all these modules in mzmine, these bioinformatics tools, easily accessible. So this tool, the MZ Wizard, it helps you to auto-generate a workflow based on the experimental setup. So you just put the information in what sampling technology did you use, with what type of detector, and what type of experiment have you done. And then you obtain a batch file for mzmine, which you then can just start. So you click create batch, you get this file, and you click start, and you basically are done with your first feature list or aligned feature list. Before we go into the first demo, let me briefly speak about lipid annotation. So why do we have an extra module for lipid annotation? Because in recent years, spectral library matching has proven to not be really reliable when it comes to lipid identification, because lipid MSMS spectra, they tend to be very, very similar, and there's a chance of over annotation in terms of structural identification. So therefore, we have this class system where we identify on species and molecular species level, which means we only identify the molecular formula and the lipid class. or we identify the side chains, but we don't go any deeper with our rule-based lipid annotation approach. Here we follow the lipid maps hierarchy, and for every lipid class, we have fragmentation rules for each expected ion notation. And on top of that, we now recently introduced an interface where you can create your own custom lipid classes. You can just define the position in the hierarchy, give it a name, define the lipid backbone, and then you can attach side chains to this backbone, as many as you want. And you can define your own custom fragmentation rules. So a fragmentation rule can be a head group fragment or a side chain fragment. And here on the top right, you can simulate these, this newly created lipid class with an example, and also can double check the fragmentation rules you have just created. And finally, for lipids, it has become crucial to have quality control checks. And for that, we have implemented a spectrum viewer where you can easily identify which signals in your MS2 spectrum have been annotated by your by the fragmentation rules. We have several plots to investigate the elution patterns of your identified lipids, for example, Kendrick mass plots. And recently, we've introduced now the equivalent carbon number plots. Here you plot lipids of the same class with the same number of double bonds or double bond equivalents against the number of total carbons in the side chains. And then you can double check, do I have the chromatography illusion profile as I expect from my reversed phase chromatography? So with that all in mind, let's jump into mzmine for the first demo. So before we start processing with the wizard, I can easily import raw data via drag and drop into mzmine. And now I have imported 3 QTOF data sets from a lipid extract from blood plasma. Here I can now use the raw data overview by right-click, show raw data overview. And now I can investigate the chromatography. I can have a look at the noise levels, and these 2 informations, they are quite important for setting up the MZ wizard. Here in this data set, kindly provided by Michael Witting, this is acquired on a xenotoph, by the way. I can see here already in the in this table that it is a DDA method. So I have MS1 scans and then always 3 MS2s and then an MS1 scan again. And this gives me also some information about what I have to do in the wizard. So with that information, I can directly jump into the wizard. I select here the experimental setup. So for us, in this case, I select UHPLC because it was a very short method with sharp peaks. I select the mass analyzer. A xenotoph is basically a QTOF, and it was DDA. The next step is to go from left to right through these steps here. I can select the raw data, which I've already done. Go through UHPLC tab. Here I add some information about my chromatography. These are the defaults, and they will work quite nicely already. So I will not change anything here. So also for you as a reminder, the MZ wizard is there to give you a good entry point. You can later also modify and optimize each individual processing step. So then you go to the MS tab, which in this case is QTOF. So if I would change, then the tab would also change. Here it's important to add the noise levels, which we can obtain from the raw data visualizer, and the mass accuracies. I can filter here for many samples. If, for example, I have a large data set, here I just have 3 example files, so I don't need to really remove anything. And important here now is the annotation tab. So we don't have any spectral libraries. We don't have any CSV file where we can do MS1 annotations with. We just want to identify the lipids. And in the last tab, which corresponds to the experiment, Here it's DDA. I can select different exports for other tools, but in my case, I only want to do networking. So I just click now on Create Batch to get the batch mode here. On the right-hand side, I have the correct order of all the modules I need. And on the left-hand side are all the other mzmine modules I could now add to enrich my batch queue. As I said, we can now still modify all the details. So for example, I can double click on lipid annotation. And here I can see the lipid classes that are currently in my search scope. I can then also modify further the search scope by setting up the side chains I will look for. So for example, here I look for 6 minimum and 26 maximum side chains and 0 to 6 double bond equivalents. And for the matching, it's important to give an MS1 accuracy. So let's say 5 ppm is quite reasonable for high resolution mass spectrometry. And the most important parameter for LC-MS-MS data here is search for lipid class-specific fragments in the MS-MS spectra. And here I can give another MZ tolerance, and I can give an explained intensity threshold. So this means the fragmentation rules now have to at least explain 40% of the whole intensity in an MS2 spectrum to create a lipid annotation. So, and if I click OK now, then the processing starts of these 3 files, and I obtain the final feature list. So I just went to the feature list tab and opened the feature list. Here you can see the overlay of these 3 samples. And if I now click on the lipid annotation column, which was added by the lipid annotation module, I can sort by annotation. And I can also see the other information I get from this module. So I get also the adduct, the formula, the MS1 accuracy, and the explained intensity. Now to get a better overview, now first of all, to check the quality, I can right-click on the feature and say, show matched lipid signals. And then I get these MS2 spectra with matched signals. And these matched signals here, they help me to understand why did I find this triacylglycerol with 80, 16, 0, and 18.1, because this is exactly what these side chain neutral losses point to. But this spectrum here is really crowded. It's chimeric in this case. So there are many triacylglycerols actually present in this spectrum. And that's why we get multiple annotations with different side chain combinations. Okay. We now also have the opportunity or the possibility to look at the lipid annotation summary for this feature list. For this, we can either use the quick search. For example, you press Command F or Control F, and then you can just type lipid, and you get access to the lipid annotation summary module. You also can access this plot using the menus on top, the visualization menu, feature lists, and then you also find the lipid annotation summary. Here you now see 2 different sunburst plots. On the left-hand side, you see all lipid annotations, so also counting for the multiple annotations. So that's why we currently see here 257 triacylglycerol annotations. And on the right-hand side, we only see the total number of unique lipid annotations. Unique lipid annotations in this context means 202 features have been annotated as a lipid. And you can filter these plots or modify them to get a quick overview on how many lipids did I find in my sample. So from here to look at the quality control tools, I again use now the quick search, and I will type ECN. And here I get my equivalent carbon number plots, which I showed in the presentation. And now I can directly see for most lipid classes, I have very nice linear trends. But if, for example, I find an example like this one here on top, where I don't really see a good linear fit, then I can look at these specific lipid annotations in detail and may spot a false positive. I can do a similar approach with the Kenrick or the 4D feature plot, which can be used as a Kenrick masked effect plot. Again, I use the quick search. I type Kenrick, and then I get this, this setup here. And now I can control all 4 dimensions of the plot, the x-axis, y-axis, but also the color scale and the bubble size. And what I am doing now, I plot the MZ against the Kenrick masked effect of hydrogen. So the Kenrick masked effect is a nice trick. You basically take an elemental composition, so it could also be CH2, but in this case, I take H, and H is by UPAC mass 1.00 something, and I define it now as exactly 1. And then I calculate the rest accordingly to this new mass scale. This, in the end, will result that all lipids that only differ in double bonds will appear on horizontal lines with an exact distance of 2. So if I look at this data point here, I can see my triacylglycerols, and I see the direct neighborhood, which only differ in the number of double bonds. And from here, I can quickly extract a new feature list by drawing a region of interest, click extract feature list, and here I now have a new feature list with only these few triacylglycerols. Okay. Lastly, for the lipids, of course, we can also do molecular networking. For this, I just right-click, show, and select feature overview in ion identity molecular networks. And what I get here, I selected a triacylglycerol. I get a big hairball of triacylglycerols. But if I select full network, I can see, okay, I have one big network for the triacylglycerols, but I get another network for the phospholipids, phosphatidylcholines. They cluster with some sphingomyelins. But I also find networks which are probably not lipids, or which I at least did not identify as lipids. Here you find another one for cholesterol esters, for example. Okay, with this, I like to jump back into the presentation. And I want to finish on the LC-MS side and go to the GC-MS side. And again, we do a little bit of theory and compare what's the difference to LC-MS processing, and then we jump into the live demo. So exactly the same modules are used for handling the raw data. So the raw data import and the processing of the mass spectra are done by the same modules. And the same goes for the beginning of the processing. So we again create a list of extracted ion chromatograms, and then we resolve these ion chromatograms to obtain a feature list. So again, retention time and MZ pairs. But now, since we are using GC with electron ionization, we obtain a lot of fragments per compound. Electron ionization is a so-called hard ionization technique. It results in much more fragments compared to, for example, electrospray ionization, which is compared to EI very, very soft. So this gives us a very huge list of fragments, which on its own, they don't really have a lot of meaning. The goal here is to recombine them to a deconvoluted spectrum for each compound. And that is not easily, but it's possible because they should have the same feature shape due to the chromatographic separation, because the fragmentation happens in the ion source. So that's the first difference to the LC-MS processing. Then for the alignment, it's also a different approach. We cannot really use the MZ value. What we do is we group by retention time across samples, and then we compare the similarity between the deconvoluted spectra from the different samples. And if the similarity and the retention time are in an appropriate window, then we align these samples. So we can then use also these deconvoluted spectra for spectral library search, of course, we can use the same filtering modules in mzmine as we do for LC. And we can also then do the statistics, or also can even do molecular networking. One other notable difference is usually, but that depends also on the libraries you are using, you keep your isotopes when you process the GCEI-MS data. You could, in theory, filter them out as well, but usually they are part of the library spectra, and that's why you usually keep them. So how does the GCEI spectral deconvolution work? We are grouping based on the retention time range. And if we have an overlap situation like here in this pictogram, then we perform a feature shape correlation, and then we check to which group does the feature fit better. And then we add it to the group with a better score. And in the end, we have the number of grouped features, but we also need one representative feature in the feature list. And for that, we take the most intense feature of that group. So here you see a screenshot from the processing dialog in mzmine. And on top in the plot, you see the retention time against the MZ. And every colored data point here is a feature. And if they have the same color and are on top of each other, they belong to the same group. So this group here in orange creates this pseudo-deconvoluted MS1 spectrum. And here you see the overlay of these features based on their feature shape correlation. So these signals, they all belong to the same molecule. And with this spectrum, we can then also perform the alignment. So this deconvoluted spectrum is then used in the alignment process, where we again group by retention time and then compare these two spectra. One important thing here, sometimes it's a rare case, but it can happen. Sometimes you have same RT group, a fitting match, but not the same MZ value as most intense signal. And then we choose the most intense shared MZ as representative feature. This is important if you want to do, for example, statistics. Let's look at one example. Here we have two feature list rows. We have very narrow retention time, and we have the same mass to charge ratio. That's low resolution. That's why we have 4 zeros. And why are these not aligned? Because here, if I make a mirror plot of these two spectra, I can see, okay, these spectra are really different. So they come from different compounds. So if I would have used the joint aligner, for example, I would have misly aligned these two features. But since I'm checking the similarity of the features, I can see, okay, these don't belong together. Okay, and with this, I want to jump into the second demo. I will just close the LC data. And I go back to the MZ wizard. And here again, I can now select the sampling technique. Just as a notice, so we can also process, for example, GC chemical ionization. That's a soft ionization technique, so you can process it very similar to LC-MS. So, but we now focus on GCEI. This time we are using a low resolution instrument, quadrupole, for example. That's why we select low resolution, and the workflow here is spectral deconvolution. We again start from the beginning. We add the raw data. And now I want to explain a bit more in detail what happens in the meantime during these processing steps. So for now, I will remove the other files and will only keep one. Here, you set up the chromatography, exactly the same as you do for LC, just with different presets, because in GC you expect narrower peaks. For low res, it makes sense that the MZ tolerances are set wider. You can filter again for large studies. And here I will now select that I want to keep the original feature list, because now I'm processing one file and I want to see the intermediate steps. For identification, we can use spectral libraries GC spectral libraries. They're out there for many, many years. There's a lot of data. And spectral deconvolution, the last step, here I can say a minimum, or I can set a minimum number of signals that at least have to be in one of these deconvoluted spectra to be recognized as one compound. And I can also do the networking part. So I will quickly remove spectrum matching for my example, because now I've just processed one file. So I can also open it quickly in the raw data overview. So now I can see here I have only MS1 events. So this, you can see here only MS1. I have very narrow peaks. And if I click onto one of these peaks, I get these very crowded GCEI spectra. And let's go back to the feature lists. So we have created 7 feature lists. The first one is only extracted ion chromatograms. The third one here is resolved features. And I'm now interested, how can I go from the resolved ones to the deconvoluted feature list? So for this, I can again use the quick search, and I can just type GC, and here I have GCEI spectral deconvolution. This is the parameter setup for this module, and I have this preview functionality, which we also saw in the presentation. Go to full screen so you can read or see a little bit better. So I have 2 algorithms available. I will use the RT grouping and shape correlation. That's the one that I explained, and that's the one that's quite robust and also very fast. And now I can also say what's the minimum shape similarity I expect. And I can also set here the minimum signals in my pseudospectrum. And on the very down here at the bottom, you get a summary of the result of the module. So at the moment, I would obtain 82 number of compounds. So I would group all these features to only 82 compounds. And if I, for example, increase this number and I update my preview, I will only get 54. Yeah, and I can now click into these into this preview and investigate how does the shape correlation look like to optimize these parameters. Okay, with this, I will quickly delete the feature list. And now I will again select all the raw data files. And this time I will also keep the spectral library search, and I start the processing again. So now I'm importing 16 files. The processing is ongoing. And in the meantime, since the spectral library matching may take a few more seconds, I also have metadata for this data set, and I can go to sample metadata. And here I can see, here are the 3 plasma files from the LC data. But here's my GC data. And here I have 3 different groups. And I can use these groups, for example, to color my samples. So if I right click here, I can say color by metadata. I can say metadata grouping, and I can write here the group I want to have. So if I write group, I get the group, and then I get the color coding according to this group. Okay, let's go back to the feature list. So spectrum matching is still ongoing in the back, but we can already start investigating the results. So first of all, let's look how the deconvolution looks like. So if I scroll to the right, here I have all the aligned samples. I can right click on one of these and say, show me the pseudospectrum. And then I get the pseudospectrum with the aligned features. The same as for LCMS, I can right click on the annotation, and in this case, it was spectral library matching. I can investigate the spectral library matches. And as I mentioned, we also can do molecular networking. So we only select show, feature overview, and an identity molecular networking. And I get molecular networks from GC. So the difference here is in the algorithm, we don't use modified cosine, we just use cosine similarity. Because from the GCEI from the hard ionization from EI, we most of the time don't have a precursor in the spectrum, or we cannot be sure that the highest MZ is actually the precursor. That's why we only rely on the it's only why we rely on the similarity of the spectra. The positive side effect of these EI spectra is that we have a lot of signals. So therefore, if I now, let's focus only on the direct neighborhood. So what is actually clustering here? These are all sugars or sugar derivatives. And if I now compare the similarity, so if I select 2, then I see, okay, these compounds are actually very, very similar, and that's why they cluster. Can also obtain the full network. Here again are my sugars. I go to the right. Here I have a lot of sterols. Here's cholesterol, some other sterols, beta-sitosterol. Yeah, the data, of course, was derivativized, of course. Otherwise, you would not see these compounds in GC. Okay, let's jump back to the presentation to come to the third and final part, which is the MALDI imaging part. Let's go through the processing workflow. Raw data is handled exactly the same, but now we don't use a chromatogram builder anymore. We now have an image builder. All these imaging workflows, they also work for ion mobility imaging. Then you have an extra smoothing and resolving step. But today I will not show ion mobility data. I will only show boring MS1 data. You can then also use all the other modules we have previously used for LCMS. So we can use the isotope filtering. We can also look into the spectra to determine the isotope pattern. And we can use the same annotation modules. What's new is we also now have a co-localization module, which helps you group all these different images which have the same distribution in a tissue. One important notice to a note to the identification: spectral library search, of course, requires MS2 spectra, and most multi-imaging data is done only on MS1. We have a paper how you can do that with the timsTOF, how you can do data-dependent MS2 for imaging on timsTOF, but there are also other strategies to acquire MS2 data in imaging. So if you have MS2 data, you can definitely also use the spectral library search, but otherwise you have to rely on the local compound database search, or you can use the lipid annotation module, also on MS1 only, which I want to show in the demo. Quick look at the image builder. It follows a very similar logic as the chromatogram builder. So basically we try to extract all different MZ ratios and create a list of images. So in this case, we don't list the features, we just list the images. And the co-localization, here we try to co-localize MZ distributions, and these MZ distributions, they can come from the same molecule. It could be an in-source fragment, for example, or an isotope, but it also can come from a different molecule, which is actually localized very similar in the tissue. And we have built a visualizer to look at all the co-localized images in parallel. Or you can use the network visualizer to look at the whole data set at once. So let's jump for the last time into mzmine and go back to the wizard. So the same story. Now I select, I select that I'm using MALDI attached to a QTOF system. the data I'm showing is lipids in negative mode acquired on a timsTOF with TIMS off. And I use the imaging workflow. So I have only one file. Now I have this MALDI tab, and here I can specify the minimum number of pixels I want to have in the image. If you go too low, you get small artifact images. QTOF, still the same. Set up the intensities and the mass accuracies. And annotation, we want to do lipids. And lastly, for imaging, there's not much to set up, only if you want to co-localize or not. So let's create this, this batch file. Here you can see there are not as many complicated steps as for LCMS, but we now have to go into the lipid annotation again. And since we are doing only MS1 annotation here without verification for with an MS2 spectrum, we can mitigate false positive search by using a smaller search space, for example. So I can say in this example, I only look for glycerophospholipids. And I know, for example, that in negative mode, I will not really see phosphatidyl coli. So I can exclude them. I can also exclude glycerophosphates because they can be in-source fragments from other phospholipids. That's why it makes sense to exclude them early. Now with my side chains, I have here the option to only search for even chains. I'm looking at a brain sample from rats, so I don't really expect odd chains that may be possible due to microorganisms, but it will also include some bias and the chance of finding false positives. Now I still have the option here to search for lipid class specific fragments in MS spectra, but now I can also say keep the unconfirmed annotations. So this then results in MS1 only annotations. And if I run this now, the imaging data is now being imported, which is here, and the processing goes in the meantime. So let's look at the imaging data first. So if I double click, I don't see the raw data overview anymore. I see the image viewer. And now I see the TIC of all the all the data points. And now I have access to each single pixel. So if I click on one pixel, I get the spectrum from that specific location. And now in this image, I can select one signal, and then I get an extracted ion image. So if you don't like, for example, the paint scale, or you want to add more contrast, you can also go to Project and set Preferences, Visuals, and then you have full control about these paint scales. For example, if you want to have, I don't know, something simpler, you can use this one, and the next image you will create will have a completely different look and feel. Go back to the other one. You can also click Edit and then add custom colors. So for example, I can add another one and say I want to have like a white top, and then I have a new paint scale. Yeah, and now it has white for the most intense. Okay, so we processed the data and we have this new final feature list. And now if I sort for lipid annotations, or let's sort for the most intense ones, you can see I have MS1 based lipid annotations. And if I click on the plus sign here, I can now remove stuff that I don't need. For example, I don't have any explained intensity anymore because I don't have MS2 spectra. And by the way, we add a comment. If you do an MS1 based lipid annotation, then you get a small warning that this one was created by MS1 accuracy only. You can also remove that. And if I now right click on one of these images and say co-located images, then I get the viewer with all the co-located images for the selected one. And these plots, they are synchronized. So if I zoom in, I can zoom in all the plots at the same time and really can compare the different ion images. Okay, the last thing I like to show is how the networking looks like for imaging. I mean, molecular networking works on MS2 similarity, but what we also do in mzmine, we do a lot of MS1 shape correlations, for example, for ion identity networking. And this is exactly what we also do with the co-localization. We compare the ion shapes. So I can also now say, add the MS1 shape correlations from the co-localization module and cluster together all the molecules with the same ion distribution. I can reduce here now the neighborhood of the network, and also I can have full control about the visuals. So color retention time does not really make sense for the nodes for imaging. So I can say, show me the MZ distribution, for example. And if I now say, show me the full network, I can find more or less 3 clusters. If I select one, I can select a node and say focus again, and then I see, okay, these images, they all look very similar in terms of the ion distributions. And this network here, they should really show the opposite. Yeah, they are anti-correlated, I would say. Okay. Yeah, with this, I'm more or less at the end of this webinar. I'd like to thank my MZIO team for putting a lot of work in further improving the mzmine software. Big thank you also to the European Union and the city-state of Bremen in Germany for providing us with some nice funding to set up the MZIO company and to continue developing mzmine. And the biggest thank you goes to everyone in the audience and to the mzmine community. You see some faces here from recent developers and collaborators. Yeah, without this big community effort, this would not be possible. And lastly, if you want any more information on mzmine or mzio, you can visit one of these pages here, or we can now discuss in the panel. Thank you very much.
Awesome, Ansgar. Thanks so much for this great presentation, and especially for building this amazing tool. This is really mind-blowing to see what you can do now always with mzmine. So this is very cool, and I'm looking forward to try out some of those features. Yeah, we have plenty of time left for questions. I saw there were already many in the Q&A chat box, but if you want to ask directly, feel free to raise your hand, and then we can unmute yourself when you can ask Ansgar directly.